Hello, well, welcome back to the series of videos on pre-calculus. It feels like it's been a little while. So we're starting a new unit. We're getting out of trigonometry, thank goodness. We've been looking at trig for a long time. And we're starting a single unit on combinatorics and probability. So that's quite different than the stuff we've been looking at so far. So I want to say a little bit about what that is and why we're looking at it. All right. So combinatorics is a fancy word that really just means counting stuff. So this is all about learning how to count. But I'm not talking about the easy kind of counting 1, 2, 3, 4, and so on. I'm talking about counting things where we don't really have the option to just kind of line them up and count them normally. So what do I mean? Well, here are some example questions, right? So for example, how many possible poker hands are there? That's a question that we'll be able to answer for sure by the end of this unit, but it gets a lot harder. Like, how many configurations does a Rubik's Cube have? I was just watching a video the other day that mentioned that the number of possible Rubik's Cubes is greater than the number of grains of sand on all the Earth's beaches, right? So huge number, but still something that somehow we have the tools to be able to count. And then even crazy harder than that would be something like, how many different possible chess games are there? That's something that we definitely know to be larger than the number of atoms in the universe. And I think we can probably estimate it, but I don't think we could even come close to counting all of them, even though that number would definitely be finite. So these are really tough but fun problems, and there's kind of no limit to how hard they could potentially get, although there's a lot of fun puzzles in combinatorics. So why are we looking at it? Well, it's really important for the study of probability, which we're going to be looking at also in this unit. For example, like if you want to know the probability of getting a particular poker hand, then you need to know how many poker hands there are altogether. And probability is the foundation of statistics, right? Which is another kind of branch of math that's usually considered separate from calculus, but is something that a lot of you will, for your own careers, want to take. And usually a course in statistics would start with something like combinatorics. Okay, so what kinds of problems are we going to be looking at this unit? Well, here are some of the basic ones, like how many three-letter strings could there be in the English alphabet? Okay, so the English alphabet has 26 letters, right? A through Z. And so if I'm counting up the number of strings, a lot of these problems we're going to be thinking about as a series of choices. And here's what I mean. So when I'm making a string, by the way, that's kind of a computer science word, but that's just the same thing as like a word that has 3 letters, but it doesn't have to be an actual word. It could just be 3 random letters, right? So when we're counting such things, I'm going to think, well, okay, I have 26 letters that I could put in the first slot. Okay, I'm testing out this new tablet that I just got, so sorry if my handwriting is going to be a little wonky. So that's how many choices I have for the first slot. But for each of those choices for the first slot, I could pick 26 letters for the second, right? There's no restriction given what I picked first on what I picked second. So that's 26 times 26. And then for each of those choices, I've got 26 choices for the third slot. Okay. You can think of this as kind of massive branching tree, right? For every letter A through Z that I pick for the first one, I'm going to have 26 branches coming off of it for the second one that I pick. And then for each of those, I would have 26 branches, giving a total of like 26 times 26 times 26 possible ends to this process, right? So that is definitely something that I would put in my calculator. I'm going to write down 26 caret 3, and I get 17,576 for that. Okay, not so bad. How does this problem change if I'm not allowed to repeat a letter twice? Okay, well, the series of choices will still work here. I've got 26 choices for the first letter. But then for each of those, now I can't pick the same letter that I picked the first time in the second time. So now for the second choice, I only have 25, right? So it's like, for example, if I pick an A for the first one, then I can't pick an A for the second one. So I've got B through Z. That's 25 possibilities. And now for the third choice, I can't pick any of the first two letters. So now I'm down to 24. Okay, so the problem changes when I'm not allowed to repeat, right? I'm going to have fewer total options. And so 26 times 25 times 24, that's not so bad. For similar problems where it gets harder, there's tricks for entering this in your calculator, which we'll talk about. But that one's easy. And I get 15,600 possible words. Okay. So this whole series of choices thing is going to be a major strategy for us. All right, so here are some important things to consider. When you're solving a combinatorics problem, you want to be asking these questions to yourself, at least until you really get the hang of it. These are three questions that are pretty much always relevant to some degree. Okay, first question is repetition allowed, right? So you've got so many slots, so many things to put in those slots. Are you allowed to repeat the same thing in two different slots? That was the difference between the first problem we looked at and the second one. And it definitely changed the answer, right? Second question is, does order matter? If I rearrange things around, do I get something that I'm considering different or not? In this last problem, yes, right? Like the string ABC is different than the string BAC. But the problem would change quite a bit if changing the order did not change the string, right? Then I would be definitely overcounting the way I was doing it. Okay, and we'll learn some strategies for when order doesn't matter. The problem gets a little bit harder, but we'll be able to deal with it. Lastly, it's important but a little bit strange. Like, are all objects considered to be distinct? Okay. In this problem, we had 26 letters. They're all different, right? Replacing one letter for another gave you a different word. In some problems we're going to look at, that's not the case, right? Changing out one thing from another isn't going to give you something that's different. So we'll see that a little bit later on, but I think all three of these are going to be questions that you want to have in your mind. And to give an example of that, here's another really basic one. In how many ways can 5 people be lined up? Okay, so I've got 5 people, and when I'm lining them up, that's basically giving me 5 different positions that they can have, right? First, second, third, fourth, and fifth. So when I'm going through these questions, I'm thinking like, okay, is repetition allowed? Can the same person occupy 2 different positions in the line? No, that doesn't make sense, right? So repetition is not allowed. Does order matter? Sure, if I rearrange the people, I get a different way of lining them up, right? And in fact, if order didn't matter, then there would really be only one way to line them up. Are all objects considered to be distinct? Well, yeah, I have 5 people and they're not interchangeable, right? So definitely yes. So in that case, with that in mind, I'm going to solve this the same way I solved the second one. And I get 5 options for the first position. After that, I'm down to 4 for the second. After the first 2, I'm down to 3 for the third position, 2 for the fourth position, and then after the first 4 are picked, then there's only one person I can pick in last place, right? Okay, so I get 5 times 4 times 3 times 2 times 1. That's one that I could just about do in my head. 20 times 3 is 60, times 2 is 120. Okay. So now that we've seen that, we are kind of ready for our first real formula. I expect that for many of us this is not going to be new, but I'm going to go over it just as if it was. If I have a positive integer, n, so that's a whole number that's positive, then I could define something called n factorial. And what all that means is, just like in that last problem, I take the number, in that case 5, and I multiply it by all the numbers that are smaller than it down to 1. So when I'm writing that out as a formula, I write that as n times n minus 1 times n minus 2 times dot 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 times 2 times 1. So easier to just think about it than to write it down in a formula. But that's something called factorial function. And as we have just seen in that last problem, it's n factorial is the number of ways that you can order n things. So thinking of it as a series of choices, that's what you get. And ordering in this way is also called a permutation. So when you see that word pop up and you say like, how many permutations are there of 15 things? Well, then it'd be just the number of ways that you can order. It's like all the possible orderings of 15 things, and that would be 15 times 14 times 13 times all the way down times 2 times 1. Okay, your calculator, of course, can do these because it gets annoying to have to type in all the separate multiplications when these are large, right? And all you have to do is, at least on a TI-84 Plus, I'm assuming the others as well, is that you hit math. You have to go all the way to the right. All the functions related to combinatorics and probability are in the rightmost tab. So you hit right 3 times to go to PRB, which stands for probability. And then you'll see that the exclamation mark, which is the factorial symbol, is down at number 4. Okay. There isn't a convention, which isn't going to matter so much right now, but will matter later. So I've talked about this for positive numbers because that's where this formula makes sense. It also is defined for 0 as well. So there 0 factorial, I mean, it doesn't make sense to take 0 and then multiply it by the numbers down to 1 because 0 is smaller than 1, in case you haven't noticed. But we still, by convention, define 0 factorial to equal 1. It's not super important to think about why, except that for many of our later formulas, this is what we want to define it as. But it's a choice that we define it that way. Numberphile has an entire like 7-minute video or something on why 0 factorial equals 1. I haven't watched the video. I don't know how interesting it is. But basically the answer is it's just the convention that makes all of our formulas work out the way that we would want them to work out. So we don't define 0 factorial equals 0 like you might think. We define it to be 1. And then just as a kind of a fun fact here, as a function, which this is, right? Something that takes an input n and gives out another number, n factorial. This is a function that grows very quickly, even faster than an exponential function. If you were to graph out n factorial as n got bigger and bigger, you could actually do this on Desmos. You can compare this to something like the function y equals 1,000,000 to the x, right? This massive exponential function that would be growing very, very quickly, but eventually the factorial function will grow faster than it. So if you kind of go far enough along, the factorial function beats any exponential. So it's kind of our like fastest function right now. Kind of cool. So here in the last couple slides, I'm going to be talking about a couple tricks to help you solve these kinds of problems, right? And we've already seen this trick in our last 3 examples, this trick of thinking of things as a series of choices. But this is a really, really powerful idea. And even in cases where it's not normally how you would think of the problem, it's a way that you can solve something much faster than you would otherwise. Okay, and I'll give you an example. This is an important enough example that I actually think you want to write it down because the answer to this matters for other problems later on, right? So let's say that we have a set. Okay, what is a set? It's a collection of stuff, just like from day 1 in this class when we were talking about functions going from like the domain set to the codomain set. So think of it as a box with some stuff in it. Say this particular set has 5 elements in it. All right, how many different subsets does it have? Okay, a subset of a set is another set, we can call it T, and the requirement is that every element of T is also an element of S. So it's a set made out of stuff that was in your original set. All right, those are the definitions we need. I know it's a little bit annoying, but these words do matter for later on. How many different subsets could there be to a 5-element set? Now, if you're trying to like think about all the possible subsets you could have, like you could categorize them, right? You could have subsets that just have one thing in it, which that you could imagine there's 5 of those, right? Sets that have 2 things in it, sets that have 3 things in it, 4 things in it, all the way up to like one subset, which would just be the original set itself. And under these rules, the original set S actually does count as a subset of itself. And then on the other extreme end, you could have a box that had nothing in it. That would also be considered a subset because everything that's in the nothing box is also in the original box. So you could try categorizing it in this way, right? And you could try counting these 5 different possibilities. That's not the easy way to solve this problem. And thinking of it as a series of choices is a powerful trick for getting a quick answer to a question like this. So when we think about it as a series of choices, what are the choices? Well, the first choice would be take element 1. There's 5 elements, so let's just label them for a second. 1, 2, 3, 4, 5. So element 1, should we put it in our subset or not? Okay, that's the choice. And the answer is either yes, we do put it in, or no, we don't put it in. And that's 2 possible choices. Okay, then we move on to element 2. Again, we decide, are we going to put it in our subset or not? That's 2 choices. Same thing for element 3. Do we put it in or not? Same for element 4. Same for element 5. So for each of the elements, we have this choice whether to put it in or not. Okay, and each of the different paths that this could take will lead to a different subset. And this is one way to construct a subset, is by this series of choices. So when we count them this way, the answer is pretty automatic. We have 2 to the 5th, so 2 times 2 times 2 times 2 times 2, that's 32. Okay, and that's really our answer, right? So that was a quick way where we didn't have to worry about counting all the 1 element sets and the 2 element sets and the 3 element sets and so on. The answer has to be 32. So that's a pretty neat trick and something that you want to have in mind for some of these really tricky problems. Okay, lastly, I want to talk about counting by subtraction, which is probably the most advanced trick, or is the most advanced trick we're going to look at today. Okay, so here's an example problem very similar to the first 2. How many 3-letter strings in the English alphabet contain at least 1 vowel? Okay, so if you're going to try to count this directly the way we've been doing by a series of choices, you're going to run into trouble, right? Because the string has to contain at least 1 vowel, but it could contain more than 1. It could contain 2 or 3. And the position of those vowels isn't predetermined, right? It could be in the first or the second or the third slot or more than 1, right? So trying to break this down as a series of choices would get very complicated quickly. So let's try to take a different tack. Instead of trying to count this directly, let's flip the question around and ask how many 3-letter strings don't contain any vowels, right? So this is exactly the opposite condition as the problem is asking. The problem is asking how many contain at least 1. How about we count how many don't contain any? Okay, and we'll see why that's useful in a second. But that's a much easier question because I'm only considering A, E, I, O, U to be vowels, by the way. I know it's like A, E, I, O, U and sometimes Y, and I thought about that, and that was annoying, so I'm just saying Y is not a vowel right now. Okay, so that means that there's 29 non-vowels, consonants. And if I'm counting the strings that don't contain any, then I just have a choice of 21 things for each of the 3 slots, right? That's easy. So 21 times 21 times 21. And 21 caret 3 equals 9261. Okay, so that's exactly the wrong thing that I'm trying to count, but here's what I can do with that, right? I already know how many total strings there are. Okay, that was 26 cubed, but I'll go ahead and look so I don't have to work that out again. So there were 17,576 total strings. And So what I want to do is I just want to remove the strings that don't contain any vowels, because I'm not considering those right now. So I'm going to subtract what I just worked on. And that means that everything left has to contain at least one vowel. So what I work that out to be, so 17,576 minus 9261, 8315. So that's my final answer. So I didn't have to count it directly. I didn't have to go into all the possibilities about how a string could contain more than one vowel or where that vowel occurred. I could imagine trying to count all those different possibilities and that being a pretty tricky problem. But by going at it sort of indirectly, I was able to find a much faster solution to it. Okay. So that's the end of this video. Next time we're going to be kind of going more in the probability direction. I'll see you then.